Hi everyone. This video is about the TX section on our May 19th, and the main topic for this video will be surface integral, and later I will talk about the problem 5 in our homework 12. Okay, so start on. So starting from before the integral, we need to know how to parameterize it, right? So just like our line integral, we know how to parameterize it. We also know how to parameterize the surface function. So first part, parametric surface and area. So now we say that we have a r with a uv, so our variable will be u and v, and in the x direction we get uv, yuv in the j direction, and our zuv in the k direction, and our uv will be in the region D and bounded in the region D in our so-called uv plane. So let's say our f, now we have f will be a scalar function, okay? So our f is a scalar function, and our ruv will be a parameterization for our surface S. So we say that the surface integral of our f on S is integral of f ds, and in definition it can be write like if you plug in your r inside it and you times the absolute value of ru cross rv, and at the end du dv. So we can also write our ds will equal to the absolute value of ru cross rv times du dv. And du dv actually is dA in this situation. And how about, so now we know the surface integral of f on S. So how about the surface area? So relatively simple, it will be you plug a 1 inside it, okay? You plug your 1 inside it, and at the end you got your integration of absolute value of ru cross rv and times the dA. So your ru here and rv here is just some partial derivative with respect to u and v. Okay. So now we know how to integrate it. We know the formula. We want to talk about some surface parameterization you will met. So the first one will be z equal to fxy. So this will be a graph that your z can be expressed as a function of f and y, x and y. So now our rxy will be what? Will be our z, because in I direction we just get z, and in j direction we get y, and in z direction we write it as fxy. So actually it's just z, but we write it as fxy. So now we want to know the absolute value of rx cross ry. Because our function r is a function of x and y. So instead of u and v, write it as x and y. Okay, so now I want to find the absolute value of rx cross ry. So we just directly do it. We with respect to differentiate it with respect to x, and we get that x partial derivative to x, we get 1, and y partial derivative to x, we get 0, and at the end our f partial x, we just, because our f is a function of x and y, so you get a partial derivative of x, and r with respect to y, we get 0, 1, and f of y similarly. So at the end, we want to conduct our cross product, so we just plug in the formula, and at the end we will get minus f of x in I direction, minus f of y in j direction, and 1 in the k direction. Okay. And you can also write it as minus f of x, minus f of y, and 1. So at the end, the absolute value will be the length of this vector. So it will be square plus fy squared plus 1. Okay. And the second situation you met is a function called x squared plus y squared plus z squared equal to a squared. So it actually is a sphere with what? With a radius equal to a. Okay, so we first recall the spherical coordinate. We find out that when we want to find a point here, so the point will be here, and the length between it and origin will be a. And how do you define the phi? The phi will be the the angle between the line with the positive y direction, okay? And also, how do we define theta? Is we want the projection of the line on the xy plane. So this will be the projection on our xy plane, and the theta we define as the angle between this line and positive z direction. Okay, so remind that now we are integrating a surface. We're not integrating a sphere. So we focus on our radius equal to a. Okay, so now our r is only the variable of the function of phi and theta, not the function of radius. So we get a sine phi and cosine theta in I direction, and a sine phi sine theta in j direction, and at the end a cosine phi in the k direction, and our phi is from 0 to pi, okay, and our theta is from 0 to 2 pi. Okay, so similarly, we want to conduct our r partial derivative phi cross our r partial derivative to theta, and we want the absolute value of it. So we just conduct it similarly as we done in this page. So just conduct it, and by formula you will get at the end, you will be a squared sine phi times a sine blah blah blah, just this. So this will be the whole of the vector, and we want the absolute value, so it will be the length of it. So you just use the same formula, and you notice that there's a sine phi in the I think it's sine phi sine theta. So you get cosine theta here and sine theta here. So this 2 square root plus you will get a sine phi square, and is a cosine phi square. So at the end you'll get this one. So the absolute value of the cross product will be a squared plus sine phi. And recall that in the calculus 3, when you're conducting spherical coordinate, you need to compute Jacobian, right? So you also know that the Jacobian will be this one. So it pretty much is the same thing. Okay. Okay, so the third part will be x squared plus y squared equal to a squared. So actually it's what? It's a cylinder. Cylinder. With what? With our radius equal to a. Okay, so now we know that our z is in here. This is our z direction, right? And our theta is defined as the angle between. I think. Oh, this is wrong, so it should be like this. Should be like x, y, z. Okay. X, y, z. So I just some wrong interpretation, but okay. So the theta will be the angle between the line and with a positive x direction. Okay, so now similarly we conduct our parameterization. So our r, because we're now integrating a surface, so our radius is constant, is a. So we got a cosine theta I in I direction, and a sine theta in j direction, and finally z in the k direction. So our r theta cross rz will be a cosine theta in I direction and a sine theta in j direction. Okay, and at the end you take the absolute value, you will get a. So also recall the Jacobian in what? In cylindrical coordinate will equal to r. Okay, so I here r will equal to a. Okay, so the next part will be kind of a surface integral. It will be flux integral, and it is some application in physics, so it will be one important class. Okay, one of the surface integral. So now we say that our f is a continuous vector field. Okay, so now our F is a vector. It's a vector, and on an oriented surface S, and we say that it had a unit normal vector. Unit normal vector, n equal to RU cross RV subtracted by the length of it. Okay, so we say that the flux integral of our F across the surface S is defined to be like this. So is your vector F inner product. Okay, so because now our N and our F is both a vector, so this will be your inner product. Okay, inner product. Okay, and it will also equal to what? Because we know that from this page we get our ds equal to the absolute value times dA. Okay, so we come back to here, we plug in, so we get our F times N, and we also know our N is this one, so this will be RU cross RV, the absolute value of it, times our ds changed to this one, so we get RU cross RV times dA. So we can subtract by this. You can subtract by this too. And at the end you will get this one. So this will be our F in inner product another vector, because we know that the cross product is another vector. Okay, so let me clear this up. Okay, and just some note is that when our F, because now is a vector field, when this vector field represent the velocity field of our fluid, then the flux integral will measure the rate fluid flow across the given surface. Okay, and now we have a new term, n, right? So let's go back to conduct the n in these parameterization. So first part, our n will be in spherical coordinates. Your n will be, because we know that n is this one, subtract by this one, subtract by this one, right? So our n will be, just plug in the formula, try by its absolute value, and at the end we'll get n equal to, assume that this subtract by this one, you only get the last term, right? So the last term will be sine phi cosine theta in the I direction, and also our sine phi sine theta in J direction, and cosine phi in K direction. Okay, so all this will be our n in the spherical coordinate, and you can notice that it was outward. So n is pointing outward, okay? And in cylindrical coordinates, your n, by definition, it would be cosine theta I plus sine theta j. And also notice that it will be outward. Okay, so it will be pointing like this. And it will be orthogonal to the surface. So it will also be outward. Okay. So this will be most of the part of the concept of surface integral. And now let's do our problem 5 in homework 12 together. So in this question, the surface is formed by a union. So it's a union of what? Of two spherical surface. And it tells us that it oriented outwards. And our vector field, F, will be 1, 1, and z squared. So this is a vector field. Okay, so the first part, A part. The lower part, S1. So this one will be S1. Of the surface is part of the sphere x squared plus y squared plus z squared equal to 1. So we know that our r now equal to 1. That lies below the plane z equal to 1 over 2. And I want you to find the flux of f across our S1. So the first part is to decide whether our S1 is. So now we cut. Okay, we have a knife here. Okay, we cut it through our YZ plane. Okay, cut it through YZ plane. And what we got is YZ plane. YZ. Okay, so our YZ plane. And you know that because it tell you our S1 is a sphere in, you know that the origin is in the 0, 0, 0, and the center will be in the origin, so the radius 1. So we get this one, S1, and this will be origin, and your R will be 1. So get 1 here, okay? So get 1 here. Okay, so now, before we parameterize the surface, we need to know how the limit goes, right? So it will be from this part. So notice that this part, the part upper to the z equal to 1 over 2 will not be compute. So actually, the surface will be, S1 will be this part. Okay, so this will be our S1. So we want to know our theta and our phi. Okay, so theta we know that because we are circling around, so our theta will be 0 to 2 pi. So the important part will be our phi. So the limit point will be in this 2 points. So we draw a line from here to origin. And we know that this part, because our z equal to 1 over 2. So this will be 1 over 2. And our radius here will be 1. So we know that this, our phi, will be pi over 3. Okay? So now we know limits, and we know from this section we know how to parameterize it. So now we can compute the flux integral. We can use first one. We can first use this. Okay? We first use this one. Okay? So now integrating in the surface S1. So we plug in this formula. This one. So our vector field F will be 1 and 1 and cosine. Because now our XYZ, notice that it will be sine theta cosine. Will be, I think is sine phi cosine theta and sine phi sine theta and cosine phi. Okay? So you plug in XYZ and you get 1 1 and cosine phi squared, because our A is not 1. And times what? The inner product is the cross product of these two, right? The cross product of our RU and RV. And in spherical coordinate is R phi cross R theta. So it will be this one. You just plug in it. It will be this one. Okay. So you just plug in it and get your A equal to 1. So you will get this sine squared cosine and sine squared sine theta and your sine phi cosine phi. Okay, and at the end is theta d phi. Okay, and just draw a line here to, okay, So because we inside is d theta, so our theta is 0 to 2 pi, and our phi is from what? Because now we in this direction, so we know from pi over 3 to pi. Okay, so this will be our f phi, and this will be our r theta cross r phi. Okay, and so now you know how to set up integral, and the remaining will be just calculating part. So at the end you'll get minus 15 pi over 32. Okay, so this is a part in the first way, solution A. So you can also conduct it another way, because now we are doing flux integral, right? So you can also plug in this one. You can also use this formula. Okay, so notice that this is 2 vector and we are doing the inner product. So in this case, our n will equal to x, y, z, y, because our n from this part, we know that our n is equal to sine phi cosine theta, and sine phi sine theta, and at the end is cosine phi. So our n is equal to this one, but in this situation, when our a equal to 1, our x will also equal to this one. Now y will equal to 0. This one will equal to z. So our n in this case will equal to x, y, z. So make sure that it's only in this case when our a is equal to 1. So our f inner product of n will be 1 z squared inner product of x, y, z. So at the end you will get x plus y plus z cubed. Okay, so z cubed at the end, you plug in the integration, same as solution A is from pi over 3 to pi. Okay, so you plug in it, but now I want to change it to spherical coordinate, so I change it to sine phi cosine theta, and sine phi sine theta, and cosine cube. Okay, but this is not done. When you're changing the coordinate, what you do is what? Jacobian. When you're transforming your coordination, so your Jacobian is what? Is phi squared. It's not is low squared times phi. So in here our low is 1, so you times your phi, and d theta d phi. Okay, so this part will times the sine phi. So at the end you'll get the same answer, and also equal to minus 15 pi over 32. Okay, so this is A part, and for B part, it's just some same thing, but now you're integrating in the surface S2. Okay, so same stuff, we start from S2. So S2 will be from this to here. Okay, so not including the parts below the Z plane. So our phi, well, now from here, from 0, here is 0, over to here, right? So this limit point. So here will also be pi over 3. So in this case, our phi will be from 0 to what? To 2 pi over 3. And other are just same. Okay, so actually part B are just changing the limitation of integration with part A. Okay, so I think this will be all for today's TA lesson, and hope you guys catch up with the lesson, and if you have any question you can just ask professor and TA, and good luck for you guys. Thank you.